So before saying something about Yangian symmetry in relation to ADS-CFT, let me just make a few more comments on different realization of the Yangian, the so-called RTT realization. Which was, well, basically developed before Drinfeld introduced the Yangian, but not at that point the Yangian was not called the Yangian. So Yangian, Drinfeld later embedded these things into a proper mathematical framework and defined these Hopf algebra relations. But at this earlier time, Fadeev and his school already basically used it in the context of the beta ansatz. And this goes under the name RTT realization. And the idea is to define a monodromy matrix T of U by these relations here. You have an R matrix, you take some rational solution here to the Yang-Baxter equation, like Young's R matrix. And you define this T by this relation. And, well, hereby T1, T2, for instance, I mean this. Yeah, and this is again a Yang-Baxter relation. So I can again draw some picture like this. Here I have this R matrix, and then I have now two different operators sitting here, and this should equal something like this. But now I take this as a defining relations for this monodromy T. And yeah, then the idea is simply that the expansion of T, maybe up to some normalization factor, gives again the Yangian generators. So this is what you need for GLN, for example, yeah, for the algebra GLN. So say you take Young's R matrix with the tensor Casimir, where the Lie algebra generators are the generators of GLN, then you can take this. So let me write this here. GLN, you take, for instance, R to be Young's R matrix, and this is all you need, and like this you can get the generators. And if you want to look, for instance, as at SLN, then
so T is to be thought of as an operator on two sides, right? You taking two sides.
T is in principle it can act on n sides. It's like the monodromy that goes once around. This index is a, so it's again this object here, yeah, and you have one auxiliary space and n physical space.
When I have a J hat there, I should think it of a co-product.
Yes. Again, again you can define a co-product on these things.
The previous relation between the Yangian and the R matrix, it just appeared as an action on two sides. Right? Because the R matrix essentially had these terms.
The R matrix just acted on, yes, exactly. But, yeah.
T1 is T plus identity? T1?
T1 is, yes, exactly. Yeah. Okay, what you can do again is to build this monodromy matrix from Lux matrices. Yeah, Lux matrices are just a single cross, and then these Lux matrices on them each on its own will you can write here L1, L2, and this will also obey the RLL relation. So from this, it follows that the monodromy obeys this. So for S,
At the beginning also you talked about how to generating T as a generating function of Yangian, right?
yes,
That's what
exactly,
you
yes.
are,
It's this thing, exactly, yeah. Now you can turn things around and say, okay, I take this as a defining relation for my Yangian. And yeah, depending on the algebra, you may have to impose additional constraints, like here for S at n, you do it S for GLN, but with an additional plus constraint of this form, where this is usually something like the so-called quantum determinant. And yeah, since I guess you would ask this anyways, let me write down how this would look like. So this relation here, this C of u, in this case here would be quantum determinant of this monodromy matrix, which can be written in the following form. And here I should say that T is expanded in terms of these fundamental generators E here, so that I can read off these coefficients. And then this quantum determinant is the sum here over all permutations of indices alpha 1 to alpha n. The sign of the permutation times T alpha 1 at u plus n minus 1 over 2 times T 2 alpha 2 u plus n minus 3 over 2 and so on up to T n alpha n u plus 1 minus n over 2. So it's some slightly ugly relation that has to hold in addition. Yeah, just one side comment here, that this you can expand again in powers of 1 over u plus some k dk u to the minus k. And then the statement is that this dk will generate the center of the Yangian algebra.
By the way, before that, would you write this in order to get explicit solution for T, I still need to take a representation of it, right?
In this case here, yes, you should pick a representation from the start. Yeah.
So when you choose Young's R matrix,
It's a particular representation, yes.
Picking a
Yes.
action of level 1 guy. Right? That's what the Young's solution is.
Yes, yes.
So see, if I pick that representation and write down T, I will get there is right J hat, that's the trivial representation. I see.
Yeah.
No. So even when it's a trivial representation on the site set, on the single site representation, C would still be a non-trivial thing. We would have a non-local actions of J, right?
Mhm.
Coming from the co-product, coming from the fact that J hat when it acts on two sides.
This is again this bilocal thing.
It's just that the single side action is trivial. Yeah.
Yeah.
So that doesn't mean that you just truncate it to one or two, right? You still have one own
Mhm.
square
Yes,
terms, right?
exactly.
Having to do with
Yes.
the-
Yeah, okay, so this just, because it's an important thing, and if you read these old papers, people are using these relations without any reference to the Yangian, because the Yangian was introduced only late. It was only understood later that there is this Yangian algebra behind this whole construction. And yeah, that's why I thought I should mention it. And just because it's always a very important example and also interesting in the context of this generalization to n equals 4, let me just quickly give you the example of the Heisenberg spin chain, how its Yangian symmetry looks like. So the Heisenberg spin chain is just a spin chain with two SU2 fundamental spins. The Hamiltonian looks like this. I sum over a chain of spins from 1 to L. I have the identity. And again, the permutation operator. I can write explicitly down how the monodromy looks like. So say I call now my auxiliary space 0. Yeah, so I have the monodromy is something like this. This is now my space 0, and here I have 1 to L. And I can write down the monodromy in terms of Lux operators, U, which solves the RTT relation with the Lux matrix LK0. So let me write it really explicitly of U. And now I have, just some, for convenience, some prefactors here. So I have an identity acting on the physical space times an identity acting on the auxiliary space plus I JKA, and this will be now my physical representation times my fundamental representation, which are contracted. And yeah, in this particular case here, I will just choose this here to be again the Pauli matrices, and also this will be the Pauli matrices, and the difference is just some, for convenience, some normalization. In other cases, like for instance, I will mention this later for scattering amplitudes or whatever, these would be differential operators acting on the momenta or something. So this is always the physical space, and this is some auxiliary space. In principle, you can put your arbitrary representations. In practice here, you have mainly the fundamental representation. And given this definition of the Lux matrix, I know it solves the RTT relations. I can plug this in here, and then I can really sit down and see what I get. Just to do this at least once explicitly to see how this expansion that I always schematically write really looks like. So at first order, I really get JA, my standard Pauli matrices, and then at higher order, U square epsilon A B C, sum J smaller k, J J B, J K C. And this whole thing would be tensored with my E naught alpha beta. And actually, when I wrote this expansion, and when you try to reproduce this, you will see that at this order 1 over U square, you will also get additional Casimirs of the level 0 symmetry, so some J square. This doesn't change the property of T to be conserved, and it doesn't really change the algebra. It's just if you try to reproduce this, you will get these additional terms. You just do not just get this, but you also get some J square here. Just to say this explicitly, and then you get these higher terms. But here you can really very explicitly do this just using Pauli matrices and checking what you get. And just for completeness, I should maybe also mention that you can formulate the integrability here also in a different way, namely you can look at it's Young's R matrix.
So it's conceivable that the representation of Yangian that you are
Well, and
So in the Young matrix, the Yangian, the relation of the Yangian was given by specifying that it just acts trivially on a single site that everyone generated. That's 0. So that's what you get in here. 1 over u square just has that.
exactly,
piece
exactly. Yes,
and
yes,
does
yes.
not have a
Yes.
does not have a local piece.
Yeah.
You don't really to set something not a place where you have actually a non-trivial representation of one that is on a single site. I mean, if there are certain examples, does that mean that this is unique?
Okay, an example of this were my fishnet diagrams from Monday, right?
Okay.
There I had these integer evaluation parameters in front, and then yeah, a non-trivial single site.
Just that. But then I think of that as starting from this trivial representation and use the automatic.
Yes, but this is where this local term comes from, right? The local single. Okay. Yeah, if you want a more complicated example, yeah, as I said, for example, these things on the action where you have a single site representation where, I don't know, P maps one field to two fields, something like this. It's conceivable. Okay, this is non-local charges that I get from expanding the monodromy around infinity. What I can also do is to take the trace of the monodromy, trace in this auxiliary space, yeah. So here I had looked at this, and here I look at this, and now I really take the trace here. So trace of T of u, and this can be written schematically like this. Qn, yeah. And in this language, this h here is just q2, and it's q2 because this acts on two neighboring sides, yeah. So I have k, it's a two-side interaction, yeah. And what I will generate here are conserved charges, a whole tower of local conserved charges, where local means that it only acts on neighboring sides. So this thing here is always something like this: sum over k, some interaction. This here acts on the kth leg, and the number of terms that are interacting are n. Yeah. So the higher the order, the longer the interaction here becomes. And this is an alternative way of thinking of the integrability. All of these qn's commute with the Hamiltonian. This guarantees you that you have integrability. This gives you higher conservation laws. Whereas for the Yangian level 1, the integrability statement would be that J hat with the Hamiltonian commutes up to boundary terms. Yeah. It does not commute exactly, it commutes only up to boundary terms. So these are level 0 densities acting on the first and the last side. Still, this is a non-trivial constraint on the bulk Hamiltonian, and this is really what's behind the integrability.
Why is it that you take with this T in terms of the system, you take log of it, you get just the local charges? It was very, I don't see why.
It's not trivial to see. I think, yeah. I'm not even sure there is a general proof for arbitrary models that these charges are local. There are some proofs for specific models, but yeah. And yeah, let me just say that since I emphasized this before, that now this boost which in this context is just the first moment of the Hamiltonian. This will act on the on the monodromy like this, namely exactly as the shift in the spectral parameter. Yeah. And this shows that the boost is a raising operator for the local charges and a lowering operator for the Yangian. Where lowering operator for the Yangian means exactly what we've seen before, namely that B of J hat something like J, and yeah, you can apply this to general levels, n goes to n minus 1. Okay, now let me say some words about the Yangian in ADS-CFT. Okay, what we want to look at is strings on ADS 5 times S5 dual to n equals 4 superhang-Mills theory, which both have the Lie algebra symmetry 2,2/4. So here this is the symmetry of the Lagrangian, and here these are the isometries. And yeah, one can now, as you know, compare different quantities like the spectrum in both theories and so on. And just a few more explicit comments. So for strings, if one takes the light cone gauge and an infinite worldsheet, then this results in a 2D worldsheet QFT. So you have questions on this? Yes. It's a symmetry in this sense. The spectrum does not organize into multiplets of the Yangian because it does not exactly commute. Still, yeah, I would say it's a symmetry of the. Sorry, is? Yes. Up to boundary terms. I think you will get the same problem. Like for the in this 2D field theory, my assumption was always that the currents go to zero at infinity, right? And this is the same effect here. If you look at the infinite spin chain, you have no problems. If you go to a finite chain, you always find these boundary terms.
This boundary term is something like the integral of the normal current over the sphere at infinity. And the sphere at infinity in this case is just 2 points. So one.
Yeah, in 2 dimensions. Yeah.
The continuum in general dimensions.
Well, we don't even know how to formulate this thing in general dimensions, right?
But I'm just trying to implicitly understand this term that it takes. It's like a flux. It's like a current flux.
Okay, here one gets on the worldsheet such a 2D curve T, and after this gauge fixing here, the residual symmetry, so residual means the leftover symmetry from this here is SU2/2 squared, and you can also show that the equations of motion admit a Lux representation, and yeah, you like this you find infinitely many conserved charges, as was shown by people in the room and then extended to the supersymmetric case by Bena, Polczynski, Reuber. Yeah, so just these superficial comments. On the string side, let me also make a few comments on the gauge side, just to get an overall idea what one wants to compare. So on the gauge theory side, we want to look at, for example, if we want to compare the string spectrum to the gauge spectrum, we want to look at the spectrum of gauge invariant local operators. Which are traces over the our fields, and these phi's here just represent any of the fields in the theory, and these fields here transform under the symmetry algebra of the theory, which is PSU2,2/4. And yeah, as you see, this is just a lattice of spaces transforming under a symmetry, so you can also call this a spin chain. Just with the additional constraint that it has to be invariant under cyclic shifts, because that's a property of the trace. Yeah. And then here it turns out that the one loop dilatation operator, which gives me the spectrum is nothing else than a PSU2,2/4 spin chain Hamiltonian, and the S matrix on this spin chain has residual symmetry SU2/2 square. Yeah, so these are just some overall facts. Let me now give you some more specific. To the worldsheet S matrix. Oh, you mean in the gauge theory side? This is the gauge theory side. Yes, yes, yes. Yes. Okay, the dilatation operator acts on this spin chain.
Yes.
Yeah, I can diagonalize. Okay, this is, if you're not familiar with this, probably too quick. You can diagonalize the dilatation operator by making the beta ansatz, yeah?
Yes.
And in the beta ansatz, you scatter excitations on the spin chain. And this is the S matrix for the scattering of these excitations.
Quantum symmetry.
You have PSU2, you have, exactly.
Breaking that symmetry to that, and now the excitations about that vacuum will are only expected to have that small.
And what does this statement correspond to in actual representation? That this S matrix has this symmetry. This is some S matrix with a spin chain.
Yes.
And you have this
well, you can use this S matrix. So you take the 2 to 2 S matrix, you construct higher point S matrices, and with these you can build up the eigenstates of the dilatation operator and diagonalize the dilatation operator, which gives me the spectrum of the theory. Yes.
You don't think of actually scattering the use that S matrix in the data to diagonalize the dilatation operator. So
This is not the external S matrix, this is some internal S matrix. Yeah. But this is also exactly the S matrix that's responsible for the two-dimensional picture in NFS4. Yeah? So again, it lives on these traces here. And these traces are the one space dimension of the 2D theories about which I've been talking the last two lectures. Yeah? Okay. So let's look at this S matrix in a bit more detail. What this S matrix is calculating?
What is it mean? What question is it answering?
It's the scattering matrix for excitations on the spin chain. So this might, sorry? Yeah.
What are the different states of each spin? Different values of different doses of it?
I think this will become more clear when I talk about this quantity you're asking about. So this is now this internal S matrix. And it turns out that the full spin chain S matrix here, you see you have this nice SU2/2 squared symmetry, actually factorizes into a 2 SU2/2 invariant S matrices, so it's useful to just restrict to one copy if you want to understand the S matrix. And in order to do this, one can consider
why does it factorize like this? And appear you expect other terms, right? So factor plus another factor.
well, sorry, there is an overall function of the rapidities, but why does it factorize like this? It happens to so if we want to study this, it makes sense to look at an SU2/3 spin chain, which means that I look at a particular sector which is closed under renormalization, where the dilatation operator is an SU2/3 spin chain Hamiltonian, and here the spins or fields are scalar z, so phi 1, phi 2, so I have 3 scalars and 2 fermions. And now I pick this scalar z as the vacuum state, yeah, of my spin chain. So, for instance, what I have then is, for example, an excitation psi that, it depends on some momentum p, and this is a plane wave where I have here this vacuum. I have the excitation at position k, and I sum over all this. So this is just a one magnon state on the spin chain, where the spins are now named after the fields. And after I've picked this vacuum, the symmetry that will remain for the S matrix is only SU2/2. Yeah. So I have this SU2/2 residual symmetry, and the generators of this symmetry are parts of the PSU22/2 generators, SA, beta, and I have a central charge. And a very important fact about this particular spin chain is now that you have some rather unconventional effects, just schematically given like this. So if you act with a supercharge Q on an excitation psi, then this can turn into an excitation phi, yeah? But this operator will insert an extra vacuum field Z, yeah? So if this is a spin chain of length L, then this would be a chain of length L plus 1 because of this additional Z. Yeah? So what I mean here is I act on this thing, and now my Q turns the psi into a phi and adds an extra Z here.
You mean the whole space, this is psi and the space of phi as two diagonalize. But this
Yes.
externalization operator will take psi space and mix into this kind of.
Yes, yes, I will take the whole state, the whole space, yes.
So, the factor that you were considering there, so my understanding was two factors of Q2
Yes.
slash Q.
I'm now looking at one factor. This is the S matrix for this chain here, yes?
Yeah, so at least the bosonic parts of these two factors, they correspond to the two extremes. One sitting in S5 and the other
Mhm.
sitting in S5.
Mm-hmm.
So if you take the light from changes, one of the angles of S5 is equal to prime, and you were left with S3 and S3.
Mm-hmm.
So, and this particular symmetry that you're talking about is probably the S3 that corresponds to the subgroup of R symmetry. Is that right? I mean, the other one will be the.
You mean this one, this Q? Or
RAB. RAB is
yeah,
part of the O6.
yes, exactly.
And the other thing would be the
This-
rotation in
This
the
is
S5.
the Lorentz symmetry, yes,
Oh, wait.
of n equals 4, yes.
Oh, then I thought there were two copies.
No, but it's the rotation in ADS5. In the gauge theory, this will be the Lorentz generator then.
Yes, that's by Lorentz you just do rotation.
Yeah, okay. Mhm.
So phi 1, phi 2 are the two directions inside the sphere, while psi 1, psi 2 are the two directions inside inside the psi 1, psi 2 is theta Raman. So these cases this refer to both of this. I mean, I don't think
Sorry, I'm now looking at one
no,
SU2
just one
slash.
copy. They're just alpha index, not alpha not.
Yeah,
Just on the phi, not on the. No, psi. The alpha index indices are, the psi's have alpha indices,
yes.
while phi's have A indices.
So pictorially, what I have here is I have some excitation psi sitting here. I act with my Q on it and I turn it into a vacuum field and a new thing phi, a new field phi, and yeah, this is what people call length changing effects. Yeah, that occur. And this is quite unconventional. Usually if you study in quantum metaphysics a spin chain, you don't have operators that map it to a spin chain of different length. Okay, and in principle, this is not a big problem if you have an asymptotic state in a state on an excitation over on an infinite spin chain. It doesn't matter if I insert an extra z in a single particle state, yeah, because I have infinitely many anyways. Now I have infinitely many plus 1. But if I look at two excitations, this will actually make a difference. So if I act on two of these psi's, then I get something like z phi psi by acting on the first one, plus psi z phi. And now I could rewrite this, say if I have the z here on the left, I said, okay, it doesn't matter, I have infinitely many here, so I just, it's actually the same, effectively the same state as this. But here I first have to move the z to the left, which will correspond to an index shift, and I generate an extra factor e to the ip1 if p1 is the momentum of the first excitation. Yeah, so I get e to the ip1 psi phi. So one sees that in the standard language of spin chains, this will give me extra factors. This is not just a standard action tensor product of a Lie generator, but it gives me these extra factors. And algebraically, the thing that one does is to define a non-trivial coproduct delta of q, which is now this, and now I insert some additional braiding factor. Yeah. Yes.
So these Yangian kets, are they related to the operators they wrote down by state operator correspondence? Is that what you talking about? Or is it some auxiliary Hilbert space?
Where did what?
The kets you are writing.
What I wrote down before was just that this trace can be identified with the spin chain, right? Or the cats can be thought of as a trace, yeah.
Just remove those ket notation by trace of that.
So what are these operators? What are they doing? Are they changing the operators? Is it like doing some action with the transformation of the operators?
Yeah, so you consider a long operator, so trace of value in. Now those, so the goal is to diagonalize the definition, compute the spectrum of the definition of the operator for this time.
What do you compute spectrum of relation operator? You compute it in the original Hilbert space.
Because we have some operators at classical level that we know that the probability, the quantum mechanically we get corrections,
Right.
and the job is to compute those corrections.
Oh, you want character. Okay.
So let's say you have a bunch of files, because of previous condition this will not get normalized, eventually this takes place. Now let's say let's consider an operator, not all files, but let's say two sides.
Okay.
Okay. Now this two sides is not going to be with some fixed number of files in the middle.
Right.
That's not going to be the eigen state of the relation of this.
Right.
So he's telling this whole computer.
Okay.
Well, at the moment,
These sides and so on. So,
at the moment, I'm actually interested in understanding the scattering matrix on this thing, right?
yeah.
Because this is what we already did before.
So that serves as an intermediate to computational tools to get to that spectrum, because once you have the scattering matrices, you can use that scattering matrix and for plugging into the advanced circuit.
What is the scattering matrix? What is it computing?
It computes the scattering of, where is it? These excitations, yeah? So I have different excitations on my spin chain. These are plane waves on the spin chain. They can have a momentum, they can propagate here on the spin chain. And now they can scatter.
Okay, so the Hamilton on this space with the relation operator, and in original language, revolution by Hamilton is taking a H on ket actually translates to H comma operator. Is that right?
And what is a comma?
H commutator operator.
H.
What is
in the same way as for the Heisenberg chain that I've shown you before. You have this sum.
But what does it mean in the original language?
It's saying that if you're a state, you can apply e to the minus I. On the other hand, if you have an operator, then you allow it to apply e to the minus I.
Okay, these are states. These are
It's actually an
What,
operator.
what
yeah, but in my spin chain picture they are states.
Okay, but so now what is the Hamiltonian?
The dilatation operator.
But all the
I will tell you more, some more things about the Hamiltonian. It's like for the Heisenberg spin chain, in a particular sector where you have only two scalars here, it's exactly the Heisenberg spin chain Hamiltonian. So 1 minus permutation that acts as a sum.
no, but in this thing,
Yeah, this is an eigenvalue.
so when you write H on K, in the original language it means H commutator operator.
Yeah.
Are there no problems with linearity in this? Oh yeah, sorry, we can't do it. Sorry, I didn't.
No problem. Yeah. Of course, there's a there's a long history behind this. There's a history of the adaptation of old integrability methods to ADS-CFT, and before that, there was already the development of integrability methods in quantum metaphysics. And yeah, actually, you would have to understand these things before, really learning what how these things work in ADS-CFT. But I guess this would take even more lectures then. But I understand the questions, yeah. So the idea is you observe that the action now of this supercharge, for example, changes the length in this way, and I want to take care of this in an algebraic way by defining a coproduct like this, where I now add an additional algebraic element, which is this braiding factor. And you see that this braiding factor in this context here, so here this U for Q should be identified with e to the IP. Yeah. So if I now act on this state, on this particle state here, then this U will measure the momentum of the first particle and insert this thing. And this means, now here with this Q twiddle, it does not act anymore like my original Q, that it inserts this Z, but this Q twiddle will just act in the standard form, namely in this way. So what I've done, I've rewritten this length changing effect in terms of a non-trivial coproduct for this Q. And this this is then what people have called dynamic representation, because now the coproduct is not the standard coproduct for a Lie algebra generator anymore, but already at the level 0, these are just the Lie algebra generators. It's non-local, right? Because it acts on two particles. So generically, what I have now is JA has a coproduct of this type, and J hat A will actually inherit such a thing. In this form. And for this particular algebra, here I've only given the example of the braiding factor for Q, but I would have to generalize this to other algebra elements. So for the SU2/2 algebra that I've shown you, I have here the braiding, the power is 0. So actually this number here just corresponds to the factor here in front, so to the power of e to the IP that I get. And moreover, I have q where I get +1, which is what I've shown you there, and s as -1. And then there's an important thing that actually, if you look at the algebra, things are now only consistent if you centrally extend the algebra. So what you need to do is to, before you had something like q was actually 0, and I have to introduce the central extension p.
How do you motivate the u factor in the bilateral
My motivation, the motivation that I gave was only this one. But the level 1 generator will have, if you try to understand what the algebraic meaning of this is, will get a similar factor. So this is something like twisting the whole Lie algebra and thereby also twisting the Yangian symmetry. And the twist depends even on the momentum.
What I don't understand is that twist in the level 0 generator canonically maps. Okay, the first line, the first part of level 1 I understand. With the second part, the FABC part, that the twist maps like that. That's what I don't see. Maybe some substance support that you have.
I don't know. Basically, at every point in this coproduct where you had some 1 times j, you replace it by u times j, and yeah, here you could also have written it as 1 times j, right?
And that's not 1, it's j times j.
Yeah, it's j times 1.
Then also you could have left that there. I mean, the first term, you could have replaced that j with a u times j.
This j.
Or upstairs.
No, but what I mean is this thing here, before it was jc times 1 times jb, right? And now I replace 1 times jb by ub times jb.
But I mean, even that perspective can be written like ja and then 1 tensor 1.
Here?
Yeah.
Yeah, but the point is that the j is on the right-hand side of the coproduct. That I replace it only if I have 1 times j. I mean, it's like here. I only introduce the u here because you see I only get 1 prefactor. I could also do it here and get rid of this. I can also define this consistently, but I make this choice. Okay, it turns out that that the braiding requires central charges, so that actually what one considers is not SU2/2, but now one looks at the double central extension, and these these two central charges here will also have a braiding that leads to this factor here, and it's given like this. Given by this. Actually, when you look at, let me write this here. So for P and K being 0, you find that the algebra implies that C, the original central charge, can only be plus minus 1/2. Yeah? And this is okay if you are at leading order in the coupling constant, but if you go to higher orders, the idea is that the central charge will play the role of the Hamiltonian. So the central charge is actually constant plus the Hamiltonian. The Hamiltonian is an expansion in the coupling constant. So if you don't allow for these non-trivial central charges, you cannot accommodate your ADS-CFT spin chain into this framework, in this algebra. Yeah?
What happens to charges? Asking that this is a homomorphism, co-product is homomorphism of the algebra.
actually, I'm not. I don't know where the Serre relations are explicitly discussed or were considered. There are several in several contexts in ADS-CFT, people consider the Yangian based on the standard coproduct, but sometimes the Serre relations are not verified simply because things become too complicated. So at that stage, it's still conjectural then that it's a Yangian. Here, I'm actually not sure whether they are considered somewhere. Well, at least I'm not aware of this particular example.
We use the standard coproduct level 0.
Yeah.
We use the standard representation. Then that is clear that they obey everything. Because
Yeah,
that's
okay.
the solution.
Okay, yeah.
I guess the question is with this twist whether they obey.
I guess one can do this because one can also formally understand this as a Reshtikin twist of Hopf algebras. So I guess this embeds naturally in a
I will just simply answer,
Hopf
we have
algebra.
an algebra and we have a coproduct. I will ask the coproduct to be the homomorphism of the algebra. That includes the constances. These are the charge elements.
Mhm.
There will be something.
Yeah, they will be modified.
Yes. Yeah, the Serre relations are sometimes very tricky, so people write in the Outlook, we leave this for future research, and this research never takes place. I don't know. In this case, I guess it might be different, but in other contexts, I'm sure that things have just not been verified or verified yet.
I'm still somewhat confused about the two factors. I thought that there was this initial work or one of the earlier work by Minahan and Garango,
Yes?
where they constructed the spin chain corresponding to some
They look just at the SO6 sector.
SO6 factor, right? And they looked at some particular, SU2 subgroup of
SO6, yes.
only that SO6. And then later on, there was some other people whose names I forget. They looked at the other, SO4, 2, which is the ADS symmetry, and found some spin chain corresponding to some non-compact subgroup of that.
You can also have a SL2 sector, for example. Yeah.
So your two factors of SU2/2 are not those two things. One.
No.
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 With the compact. So you can think of the formula that you go back to SU2, 2/4. The 2,2 is the SO4, 2. That's the SU. And the 4 is SU4 is SO6 essentially. And now pick 3 from SU4 and the SU2, 2, you just pick one of the two. So in particular you don't have gamma. Gamma is between the single non-compact. So the SU2, 2, those two SU2s were essentially the ones that act on alpha index and alpha log index. The cross ones were the P's and the K's. And now because you are just picking one of those, the cross ones you don't take. You don't have P's and K's. And now SU4 you just pick the SU2. Those are the pi's that were there.
Okay, so this is here I just wanted to emphasize that there are some special things happening in this generalization of the standard spin chain picture to the n equals 4 case, and a particularly important thing is this braiding. One thing was that I've argued that given the standard constraint relations of the Yangian for the S matrix, this implies that the S matrix is always of difference form, yeah? So this is not the standard, these are not the standard relations anymore. You have a non-trivial coproduct already at level 0, and this implies that the S matrix here is actually not of difference form. Yeah? And yeah, people have also thought about constructing some generalized boost for this, some operator that shifts the spectral parameter. And there was a recent interesting paper on this, but the object they construct is very complicated. It has a very complicated co-product. So it's really not clear how this operator sits in ADS-CFT, but it's conceivable that there is some generalization of it at least. And another important thing, which is also due to this, is that here the 2 to 2 S matrix is actually completely fixed by the level 0 symmetry already. Yeah? So even without taking level 1, you fix the 2-particle S matrix completely. Okay, so this is what I wanted to say about the S matrix. Now let me say a few more things about the dilatation operator. But in principle, yeah, it's the same idea as we discussed before. You have to identify where this two-dimensional theory is embedded in your, now in your 4-dimensional n equals 4 super mids theory, and here it lives on this color trace. And yeah, then you use similar language. You have a level 0 algebra, you find this Yangian symmetry, you have an S matrix. So in principle, the same ideas apply. So how about the dilatation operator?
Because you have a trace, so your spin change is automatically periodic. Is that right?
Periodic, yeah, and even cyclic.
Because that's a cyclic because of trace.
Yeah, I mean, it's not only periodicity, it's even cyclicity. That means it's invariant under shift, so the total momentum has to be 0.
Well, what I'm saying is that the surface charge that is got, which was the effect charge.
Right, it's a problem for the...
But that's automatically 0 now.
No, if there would be, it was J1 minus JL, but it should be J1 minus JL plus 1 to be 0, right? If I have a periodic chain, I identify L plus 1 with 1. So it's a bit more tricky.
So how do you distinguish periodic and cyclic?
Periodic means I say side 1 and L are nearest neighbors. Cyclic means the shift has to be a symmetry.
So that was anyway the translational symmetry.
Sorry, that was? Yeah, that's translational symmetry on the spin chain. So in addition to the normal beta equations, you have an equation which says that the total momentum has to be 0. Oh. Yeah, that's another unconventional thing that occurs here, which is not the case in standard spin chains. So for the dilatation operator, at one loop, as I already said, D1 is a PSU2, 2/4 spin chain Hamiltonian. So it acts actually exactly in the same way as what I've shown you for the Heisenberg spin chain, just that this is now a PSU2, 2/4 symmetric quantity. So what I can do is to specify my problem to the SU2 sector. So instead of allowing for all my fields in the spin chain, I allow only for 2 scalars, which corresponds to exactly this SU2 sector of Minna and Sarembo. And in that case, this density here is simply what we already had. So I have an identity minus permutation, which is just the Heisenberg model. Yeah. And generically, this quantity is also known at one loop for PSU2, or the whole PSU2/4 spin chain. And again, the Yangian symmetry means that this commutator turns into boundary terms. So in the bulk this is 0, but generically I get this. And this was shown in this paper by Dole, Napi, and Witten. At 2 loops, unfortunately, the full dilatation operator is not known. There are some subsectors where it's known, but generically it's a very hard problem, and it's not has not been determined. So what I want to do, at least, there are also some other sectors where it's known, like this SU2/3 sector, but not the full theory. So what I want to look at is in the following now, again, this SU2 sector, where I have only 2 scalar fields, and there the dilatation operator is known. And in my pictorial language, it's just this 3 times the identity plus 4 times permutation minus such a permutation. Yeah? They're what? Yeah, right. That's true. So this is the 2-loop contribution to the SU2 sector dilatation operator. And in principle, in the SU2 sector, one can also determine it or give it at higher orders.
Just to understand if I understood correctly, so this identity should be drawn as 3 lines, 3 vertical
Yes,
lines.
yes, in principle.
And the second one is 1 vertical line and the cross, and the other one is.
Yeah.
So
On a periodic chain, it will actually not matter whether I draw the boundary
which way
lines.
you draw it, yeah.
Yeah.
And 4, I mean, so this 3, 4, and minus, so this can be just understood as 2 insertions of the commutators where interaction, I mean, how do I know that what's the correspondence with 2 loops in the Yangian series, right? So
The interaction range here.
yes,
So at 1 loop, I was acting on 2. So 1 vertex was allowed basically, and here I act on 3 legs. So the principle is like in Feynman diagrams. The more vertices you have, the more powers of coupling.
yeah. So this is like the D1 is like 1 insertion of the commutator in the Yangian series. And the commutator has, I mean, I think I'm some kind of vague understanding of where this position should be met. There is this leeway, kind of. Never mind. I think
you just draw a diagram with the row and three.
Yeah.
Like that, right?
that's right. So
Similarly, because it's the two,
Yeah.
they have more things to work with. So there will be a term where all 3 things will stop. So by the way, in this D2, D1 square is already included, or that's separate?
It's a separate thing. There's no D1 square in this thing. Yeah. So how about the Yangian symmetry? And I stay in this SU2 sector now.
So if I take a look at this one diagram, then I will understand the key. I thought it was just successive commutator. Yeah, what is this?
Gluon diagrams. So this actually
Feynman that's an effective interaction, right? So if you stick with this SU2 sector, so there is all these sites could either be phi 1 or phi 2. And now if you take, let's say, 3 pi, and then C, after 2 interactions from gluons, what can you get? The claim is that you can get everything that is in the given bar.
Okay, actually, I should probably write somewhere that the expansion of the my notation is now that it starts at one loop, so lambda is the top coupling, and yeah, this is D1 and D2. So the level 0 symmetry is actually exact at all orders, yeah, and this is what tells me that I can write things in permutation symbols. As we already did for this SU2 S matrix, we said, okay, SU2 symmetry means I have 1 minus permutation. In general, here now all my building blocks are permutations, and in principle I just have to determine the coefficients. For the level 1 symmetry, it's a bit different because also the level 1 generators become coupling dependent. So if I look at this thing here at order lambda, then well, and this one is actually now not the level but the coefficient in the expansion. Yeah. So JA hat will now also be JA1 plus lambda hat 2, yeah, and so on. So yeah, I have a slightly more complicated constraint equation, and this will be 0 again up to boundary terms. And actually the explicit expansion for this J hat can also be determined, and for instance at leading order, yeah, let me write this here, this J hat looks like this: epsilon ABC, J smaller k, JJ, JJB, JKC, plus, and now you have the correction in lambda, epsilon ABC, sum over k, J KB, JK plus 1 C, plus higher orders in lambda, yeah? So this is the standard thing you know. This is the symmetry of the one-loop dilatation operator. And in order to satisfy this equation with this two-loop dilatation operator there, I have to add such a term, which is the nearest neighbor term, yeah? So it has the same structure as this thing, just that now I fix here J to be K minus 1.
Sorry, I don't understand. I thought the whole Yangian symmetry should be understood as something that is generated by J hat, and a particular coproduct. Right? Now, can I just understand this in that notation, in the first realization of Yangian?
I guess yes. I guess this is your non-trivial example of a.
Okay, good. Good. So that should
Yes.
be thought of as the local piece.
Yes.
So that's
Well,
like
yeah,
the
but it's
evaluation.
not strictly local. It's nearest neighbor, but
It's still local, right? So
yeah.
that's like the evaluation replaces the evaluation.
Yes, yes.
Okay, good. Oh, that's right.
But it's also quite unconventional. It's really adapted to n equals 4 and has. I don't think this. Yeah.
No, but at least.
Yeah.
And now you're saying all these lambda squares are kind of local pieces,
Mm-hmm.
but they're better to be advanced. Yeah. Okay.
And yeah, actually it turns out that one, for this SU2 sector, one can find can find a recursive definition here.
Okay.
So for the dilatation operator, as for the and in principle, I can also write down all the higher terms. I can write this down exactly. I just have to modify this connection here. Yeah? So this is a bit like a parallel transport equation for the dilatation operator in the coupling constant now. Yeah? I will tell you. And the same holds for the Yangian level 1 generator. Yeah, and then this equation will be satisfied. So what is B3? From before, you remember this equation. Yeah, where we had this boost operator that shifts the spectral parameter. Now B3 here actually is something like a higher boost. So in analogy to the boost that I had before, where I had here the Hamiltonian, the charge Q2, I now take the next higher local charge, Q3, put the K in front, and this defines this boost. This generalized boost, yeah. And yeah, okay, if you also want to see how Q3 looks like, it has this form as a permutation operator. Yeah, so in this SU2 sector, in principle, you can generate, well, you can just solve these equations, and you can do this really up to, I don't know, 15 loops or so. So you can get all the higher terms in the dilatation operator and all the corrections to the Yangian generators, and in principle, yeah, this is even guaranteed to be integrable because you can define things in this way. Of course, you cannot check that it's the correct result because you cannot do the field theory calculation, but
How are you getting your equation one two calculation? How do you know this differentiation is correct after all this?
okay, I cannot prove that it's correct. Okay, the statement is that with this method you can construct integrable spin chain Hamiltonians and the respective long-range spin chain Hamiltonians and the respective Yangian symmetry. What you have here in general, you can put some arbitrary coefficients, and now you can match these coefficients to the beta ansatz of n equals 4, and then is the SU2 sector of n equals 4 fits well in this picture. So if it's an integrable spin chain Hamiltonian to higher loops, then it has to be this.
You assume that. Yeah. So how does one do this calculation? Get all the corrections?
Yeah, well, I would have to tell you how this connection here looks like. What will happen is that also the higher boosts, not only B3 enters, but also higher boosts, and a second type of generator.
What I'm asking is, one should be able to understand this just from the representation given the Yangian also, right? This is a statement about what sort of single side representation the Yangian.
Well, single side is not really single side, right? It's nearest. It's already modifying the Yangian a bit, or the Yangian relations, I would say.
So one carries out this analysis for this modified version of the Yangian and derives a consistency condition. Is that what this type, or how would one compute this parallel square on this?
Okay, okay,
Idea.
in principle, I can give you an exact relation. I put this away. Now I don't I can specify what this x is. It depends on lambda. Well, it depends on these higher boosts and the second type of operator. And well, solving this equation gives you the higher orders, and you can really solve them in practice. Unique solution. Okay, what you have to check is that this connection will have some indices. You have to check that it's a flat connection, but you can do this also, and then you are fine. Yeah, actually, it's quite interesting. So now you can go back to what I did at the beginning, yeah, and where I introduced this. I started with the field theory boost, and I derived the conserved charge, yeah. And you remember that I had this picture where I had a 1 here, and before it was a Hamiltonian. Now I say I have a Qn here, yeah. And I said, okay, this is effectively, okay, this is something like 1 on position j and Qn on position k, and I sum over j smaller k. Yeah? Or as I defined this boost before, I sum over k, I write k Qn k. Yeah? But if I understand this picture here, then a good question is, why do I not put an additional local charge on this leg? Yeah? And in fact, this is the second type of generator that enters into this X. So I also get a generator Q, say mj, q, n, k. Yeah? And these are the two types of generators that enter here in a special combination. You have to specify this connection in terms of these. And this one, the boosts, the higher boosts, will generate deformations of the spectrum. And these ones will generate deformations of the scattering matrix. Which makes sense because here you have non-trivial densities that can see two particles at the same time. Yeah? So this will exactly generate the dressing phase in the beta ansatz, this type of generator. Okay, so much about the dilatation operator, and well, there are still many things to be understood. This, what I told you here now for the higher loops, is for the SU2 sector. As I said, not even at 2 loops the full dilatation operator is known. Some other sectors are known, but not the full one. So yeah, one starts to understand what the structure is, but it's really not.
What if one just borrow this Yangian information and understands, so you have this lambda square term, right, some explicit lambda square term.
Yes.
And now let's promote J's to be the PSU to come up with /4 generation.
Yes.
And from that derive the
It doesn't work the same way. This is for SU2. For instance, this will not hold anymore. Yeah? The level 0 generators in general will also be lambda dependent. Only the SU2 generators are 3 level exact, or 1 loop exact. Okay, then let me say some more words on Yangian and the n equals for S matrix. But now the external S matrix, so the scattering amplitudes, and this was already part of my talk on Monday. So now I'm not talking about this auxiliary S matrix on the spin chain anymore, but now I'm really talking about 4-dimensional scattering amplitudes. Yeah, and as I said already on Monday, so let's look at color ordered tree amplitudes. And after stripping off the color, I get a cyclic function that depends, as specified on Monday, on these 3 different types of variables. So lambda, lambda I are the momentum spinners. So my external momenta are given by this expression. This solves the on-shell constraints. And yeah, the etas count the helicities, so I have this superfield lambda lambda bar eta, which is, yeah, and so on. So here I have gluons, fermions, and the other particles. So these are SU4 spinners whose power corresponds to the helicity of the respective on-shell states. And yeah, as I already told you, we have the standard Yangian action that we've seen several times already. So let me just say, for example, one of the SU2/2 generators is S bar, and in this language it will be realized as this differential operator here. Yeah, and if I act on the amplitude, I put here an index I for my external legs, and I sum over all external legs, and this annihilates this color ordered amplitude. And the one dimension is the color trace that I've stripped off from this thing, which turns this into a cyclic function of the kinematic variables. So let me discuss one. Well, I guess you probably have done this exercise before. You might also. So some people might know this, or have done this themselves. So the question is, since this is a cyclic function, and we've seen that the Yangian has problems with these boundary conditions. So in principle, it's only, for example, for the Hamiltonian, it's only an exact symmetry on the infinite line. It's not clear at all that it's compatible with the cyclicity of the invariant function. Cyclicity, yeah. So the exercise one can do is to, if I call the standard Yangian action J hat being F. All right. Bye bye. So if I have the standard action F A B C sum J smaller k J J J K C B from 1 to n, then I will call this here 1 n. Yeah, so the sum here runs from 1 to n. That's the statement. And using this shorthand, I can introduce something like this. I shift the indices of the sum by n positions, and I subtract my original level 1 generator. And what one finds is this expression A, B, C, F, C, B, D, sum k from 1 to m, J, K, D, minus F, A, B, C, sum k from 1 to m, J, K, C, J, B. Yeah. So this is proportional to the level 0 generator, which is 0 on n. So the second term drops out. This thing here is C times delta AD, where this is the dual Coxeter number, which is also 0 for PSU 2,2/4 or OSP 6/4, so for n equals 4 or for ABGM. this is just the density. The M is the number of sides I shift by, not N is the number, I have an n-fold tensor product, and I want to check what happens if I do an m-side cyclic shift. So if I do a one-side cyclic shift, there will be only J acting on one position. So it's only the density.
And what are the rules there?
This thing is the full this is the full sum over all, yes. Exactly. So you see that for n equals 4, this works nicely due to this feature. So these are very special algebras which can allow for such.
Are they the only algebras?
Sorry?
Are they the only algebras?
No, I think there are a few more, but yeah, not so many. I can look. I think there's a paper where they are listed also. Can? Okay, the notation is explained here. So the level 1 generator with this index 1 and n is this sum where the sum starts at 1, it goes from 1 to n. So if I put here a and b, then the sum goes from a to b. So here it goes from 1 plus m to n plus m. Yeah, a and b are not good indices here, but I stick with 1 then.
Just to make sure, if this is not 0 for some period, so left hand side is explicitly equal to 0.
The left hand side is equal to the right hand side here.
But I can check the left hand side is equal to 0 on this one.
Yes, I guess you could also do this, yeah. But it's probably harder than looking at this expression. Yeah.
Sorry? 2 explicitly, I'm saying that it's only 0 for those special cases. The left hand side is right, but suppose left hand side gives you some number.
Yes.
In expenses. Right hand side also gives you the same number.
Yes, this is equal. This you can just compute on an algebraic level. I don't make any assumptions here. This is.
I mean, I'm sorry, just to be sure. If it is so, left hand side gives me some number, right hand side gives me some number. It's still then it will be okay, right? Like, it's still it need not be 0 always.
If the amplitude is cyclic, it should better be 0.
But suppose amplitude is not cyclic.
No, then it need not be.
But still it is a Yangian.
Well, you still have to, what you have to verify is that it's annihilated by a single j hat, right? This is just a consistency equation. So you can have an invariance equation for this thing under j hat, and this is your Yangian symmetry. But since I know that this is a cyclic function, I want to check that this has also a cyclic definition. So a definition that really on amplitudes on my invariance is cyclic. So it maps cyclic functions to cyclic functions. Okay. Yeah, and this was also a reason why people said a lot that okay, it can only work for PC2,2/4. There cannot be other algebras where you could construct such cyclic amplitudes, for example. However, if you by now we know very well that here we are allowed to add this non-trivial single side action, then here you get actually an additional term which is k from 1 to n vk minus vk minus m j ka. Yeah. So suppose the dual Coxeter number does not vanish, this term still drops out because we are looking at an invariant. I can still try to match the coefficients of of these jk here with these jk. Yeah, so I compare the coefficients here and here. So
Sorry, sir, just make a where is the in the Yangian case? Suppose I have a different theory where I have rather than say, where is the difference
Well, you have to specify the JA case, right?
No, I understand. But suppose suppose if I have a theory where, say, I'll give you one particular example. Let's say I have, say, OSP64, it's a AVGM theory, OSP64, but I make it, say, rather than external particles to be, rather than matter, I make it fundamental, say, for example.
Okay.
Then is it possible that, where does this information about adjoinness or
The J's.
which is?
All the J's here.
No, but I'm not talking about like
But here I haven't made any further assumption. I mean, I
there is
just
no assumption about representation. There is no assumption, right? So given the algebra, whatever the matter content be, it doesn't matter. But cyclicity was important. Like cyclicity, did you introduce or is it just
cyclicity is just important because my definition of this kinematical part comes from the stripping of the color trace, which was cyclic, so that this function has to be cyclic. If you don't have a cyclic color trace that you strip off, then you don't need to check this constraint.
Yeah, I guess for the fundamental particles that you have in mind, that constraint may change because
Yeah.
for atoms, right, so that they are color or
Yeah. Right. Actually, in AVGM you also only have cyclicity under double shift, so M should be 2 then.
Is the check on say AVJ theory or something? Like somebody has done
What? Amplitude?
the in AVJ those
Oh, I
are
don't know.
other than like it's bifundamental, right? Mathematics bifundamental.
Mhm.
That is probably the reason why I get the simplicity.
Well, you can also write it with a trace in front, but
Right. So I'm saying
double
suppose I
cycle.
have rather than AVJ, I have AVJ. Those are like I can take rank to be small compared to one of them. I'm just asking, has anybody checked anything for AVJ theory or no? Not that it. Those are all same equal 6, right?
that's already OSP.
So are you saying it will just go through, right? Or
Yeah, but I think we just mentioned that for those theories, because bifundamental is shift by 2.
even shift better?
That is the only thing that only can go. And does that just weaken this constraint? No, right? The constraint is still that.
yes, yes. Well, for M equal 2 then, yeah. But okay, now introducing this additional thing, I can in principle also, instead of imposing that this has to vanish, I can match this to this, so I get the constraint that this should hold. So here these are just the first M are the dual Coxeter number, and the rest has to be 0. And yeah, in general you can find solutions to this, and well, for this an application were these fishnet theories where you have graphs, I don't know, something like this, and certainly the graph is invariant under some cyclic rotation, and the underlying algebra is SO2,4, so you don't have vanishing dual Coxeter number, and then you have to switch on these, solve these conditions, and this shows you that there is is actually still a solution. Okay. This about the internal S matrix. Now I would like to finish just with two, mentioning briefly two further applications. I don't want to specify the details, just that I don't know, probably you are already aware of this, where this Yangian plays a role. So further applications in Then you put 4 super-Young mills, or ADS-CT in general. And one case where the Yangian was also identified is for the expectation value of smooth Maldassena Wilson loops. And smooth is important because then they are finite, so you don't have problems with the conformal symmetry. So these Wilson loops look like this. They depend on some contour. So d tau gauge field times x dot, and then you have this particular coupling here to the scalar field. Yeah, these are interesting because they the expectation values also correspond to minimal surfaces on the strong coupling side, where the surface ends on the boundary of ADS given by this particular contour. And yeah, you can people have studied Yangian symmetries of these, and it turns out that the expectation value is indeed invariant if you choose a specific single side action of the Yangian generators. Also there you have to really patch these parameters. And the Yangian generators are realized as functional derivatives. So, well, let me just give us an example, the level 0 momentum, which looks somehow like this. So you have some parameter that parameterizes your contour, and then you take just a functional derivative of this form. And yeah, you see that this is basically, this representation is just a generalization of the standard representation of the conformal algebra, right? Now you just sorry, I didn't understand.
If you want to go to other steps of the Wilson loop and still preserve some.
You want to go to other?
If you want to go, this is over some card C, right?
Other contours, you mean, or?
Some contours.
Yes.
Now,
with cusps or?
See, that's good, but
Yeah.
if you want to still preserve some supersymmetry, then this is not enough. You need to add some more terms. And loop by loop.
Okay, I think here you, in particular, well, at recoupling at least you also need PSU 2,2/4. Is this the question you want?
Are you talking about the supersymmetric version?
The Yangian symmetry is in the supersymmetry version, right? Oh, you are just taking, are you taking just conformal supersymmetry?
No, yeah, I'm taking, I mean PSU 2,2/4 also, yeah. The supersymmetric.
The supersymmetric Yangian, right?
Yes.
Then I think this will also be that. The thing that you put in the integral.
This is not a supersymmetric, but generic concept.
Okay, people have introduced some. Well, this is where they've first considered this problem, and there was also a paper later by Niklas Beisert and Jan Klefka and Dennis Müller, people from Berlin also, who also generalized this Wilson loop. Things become quite technical then. But they can make sense of this this Yangian invariance there. And yeah, this is very similar to this two-dimensional field theory case because, yeah, again, you have an integral, and here this parameter now plays the role of your space dimension. Okay, and then, yeah, just as a second point to mention, well, people, as we already discussed briefly, Niklas Beisert's group also considers this now for the action, where the Yangian generators are also realized as functional derivatives acting on the fields in the color trace in the action. So again, the one-dimensional space is given by the color trace, and yeah, they formulate a criterion for what Yangian symmetry of a gauge theory with this kind of action should have. Yeah, there are 3 papers by now on the market, and it's rather involved, I would say. You have to be careful with many things. Gauge symmetry in particular causes problems. Yeah, okay, so yeah, this is actually all I wanted to say. So if you want to look at some references also, I have these notes where, I mean, here in the lectures I didn't give any references. Of course, other people have done many of these things. So many references are given in this paper on the archive, these notes on Yangian symmetry, and yeah, maybe not the most recent ones, for example, for the action that just came out now, but I think all the other references should be in there. Okay, thanks.